Hello.
Hello.
Hi.
Cody.
How are you?
Hi. Lecture. Cody received his PhD from MIT. Before he joined our state, he was also on the faculty at University of Virginia. Currently, Cody is associate professor in mechanical engineering here at our state. He's interested in developing a theory and method to assure the safety and security of control systems. And applications include aviation, air traffic management, urban air mobility, and automotive. So today he's going to talk about towards autonomous systems that leverage first principles and black boxes. Cody, please.
All right, thank you. Let's see. It's a little bit weird when with multiple monitors and stuff going on. So I guess the first thing I'd like to say is, well, so thanks for having me, and it's really exciting to be part of the new center, the official center with the website and all of that. So, and I guess with that, being a translational research institute for AI, and also being very multidisciplinary, I'm going to start with actually talking about applications a little bit, and then get into some of the theory and some of the methods that we're doing. So being in mechanical engineering and having sort of a mechanical aerospace background, you get, from the very beginning, you get a sort of a philosophical approach to modeling where you write down equations, right? So you write down PDEs, for example, if you have a thermal problem or a fluids problem, you write maybe ODEs down for a lot of dynamics and control systems applications, right? And so that's been my background, and sort of that's still my perception on a lot of problems. But then we have, on the other side, machine learning and the recent advances over the last probably decade and a half with deep learning, that is so powerful, right? So, but we don't necessarily have, first principles models. So can we leverage something that we know from the physical world, whether that's intuition or whether that's a set of equations, and set that alongside of, in this case, mostly deep learning models, but other types of approaches to machine learning. And so hopefully with sort of two different threads of work, I can give two of our ideas on how to kind of leverage the best of both worlds. But before I do that, I'm running the risk of playing a video on Zoom. Let's see if this works. So, oh, and by the way, if you have any questions, I'd say no need to wait till the end, just dive in. And because I have multiple monitors, I'd say just unmute yourself and fire away with your voice with any questions.
Yeah, okay.
Uh-oh, let's see. Where did that go? So let me try this video again. So this is, can you see the video okay?
Oh, yes.
Yes,
Okay,
we can see the video.
So this is, as you could kind of see from the title, this is a YouTube video from Bangkok, Thailand. And I guess the main thing that I want to get from this is, first of all, there's tons of congestion. And there's also some, at least for somebody who's living in the US now or is from the US, some different kinds of behavior than you'd see, for example, in Ames on Lincoln Way or something, right? People kind of dodging in and out of traffic lanes. It's very multimodal. So there's this bus here on the bottom. There's vans, cars, pedestrians kind of walking up above, some below. And at one point, the camera pans up and there's a train going by. So there's a lot of stuff going on here. And it's not necessarily desirable in terms of the throughput of people that are actually able to get through the system. Cars that are sitting at idle are just spewing CO2 into the environment without achieving the objective, which is to get somewhere, right? It's noisy, so on and so forth, right? And so with this problem, there's a bunch of interesting questions that one can ask. Maybe. Okay, there we go. So there's a lot of interesting intellectual problems here. Could we go to more centralized control, build new infrastructure? Can we get better prediction, right? So if we can actually better predict what will happen, both at sort of the microscopic level of individual vehicles or motorcycles or people, but also in terms of like demand modeling and things like this, that maybe we can achieve better throughput. With the advent of autonomy, maybe with communication. So if different vehicles, different modes of transportation are actually communicating with each other, then maybe we can explicitly coordinate how things are moving about and get better throughput, lessen the environmental impact, so on and so forth, right? So the list just keeps going and going. There's so many interesting problems. There's similar problems going in air traffic. I'm not going to talk about that today, but that's a big interest of my group as well, is looking at future aviation concepts. I'm actually going to maybe play one more video and then, so let's see if this works. Okay, it's not working, that's fine. So this would be a video of amazing traffic patterns. This video is put together by the Media Lab at MIT, where all the traffic is now moving past each other perfectly and everyone's happy and everything, you know, high throughput, no one has to stop for very long, etc. But this getting to where we want to go in the future involves a couple of assumptions. One is that all the agents in the system can actually communicate with one another. And then the other is that we actually have very good prediction capability, right? So we can actually sort of see what's going to go on into the future and plan accordingly and adapt our algorithms or our control strategies accordingly. But that comes with some risks, right? So the first has to do with communications, right? So if we're relying on communication, I don't know how many of you have had a problem with cell phones or your Zoom call gets stuck. Hopefully that doesn't happen here, right? So communication is not the most reliable medium. And if we're using that for a safety critical decision, like whether a car should go or stop, that can be very risky. Here's an example of the communication, basically the packet throughput on vehicle-to-vehicle communication. And you see this little blip in the in this blue line. This is actually from two cars actually going under a bridge overpass. And due to how far apart they are and the spectrum that they're using, they basically get multi-path destructive interference, right? So there's the direct line of the communication channel, and then it's bouncing off of the bridge, and then the two waves actually destroy each other, and you get this packet loss, right? So you don't want this to happen, but unfortunately this can happen, and it happens randomly, as we've all experienced anytime we've been on our phone trying to talk or watch a YouTube video or whatever. And so we devised a solution, myself and a few collaborators, that was actually not as much interested in improving communication. There's a lot of people who are like, let's add different channels to the stack, let's improve the protocol, and so on and so forth. We were actually interested in, well, what if you could take in the scene? So at the bottom here, this is a LiDAR return from an autonomous car. If we understand something about the scene, and we understand something about the physics of the way that the communication channel, basically the EMF radiation that happens, and then the arrays of the antennas, could we actually predict what will happen with that communication channel? And so this is a little bit of an eye chart. I'm not expecting you to be able to read all this, but this is basically a recurrent deep neural network that takes in channel state information. So basically measuring what's happening at the antennas of, in this case, 2 cars. It takes in these 2 blue cars, it takes their current states, which is a 5-dimensional, right? So it's position, heading, velocity, so on and so forth. And then importantly, it actually takes the prediction of the leader and follower's future states. These would be in the future autonomous cars. So they can actually predict over the next, let's say 5 seconds or 3 seconds or whatever the prediction time horizon is, what they want to do, right? So I want to speed up and move into the right lane. And that this deep learning model will actually take all that information and predict what will happen to the channel. In this case, the packet delivery rate, how many packets get across at any given time. And it turns out that myself and my colleagues were able to do this decently well. Actually predict the packet delivery rate in a relatively controlled environment, but in theory, you might be able to do this with sufficiently powerful deep learning model. The problem is the state of this communication channel will then impact what my trajectory is, right? If I'm planning on speeding up and going into the right lane, that could negatively impact my communication channel. In this case, it could dip down to 60%, in which case I might not want to do that. So let's say I actually want to slow down. Well, that's going to change the communication prediction, which might cause me to change my trajectory and so on and so forth. So there's this tight coupling between what's actually happening physically in the environment, including with the controls of these vehicles, and then what's happening with the communication channel, and we're getting that information basically from a black box, very complex deep learning model. So that's one issue, and we'll come back to this application in a second. The other assumption about this utopian vision of transportation in the future, one is that we'll be able to rely on communication. The other is people, right? So we might be able to predict what a car is going to do if one thing, vehicle dynamics are relatively constrained, but also if they're managed by machines, the machines can just tell us what they plan on doing over a certain time horizon. With people, it's not so clear that that's how it's going to work, right? So here's a picture of or a video of people walking around in Grand Central Station in New York, and there's all kinds of complex social dynamics that happen, sort of unwritten rules, right? So people behave differently in Bangkok, Thailand, versus China, versus England, versus New York City, versus Ames. And those are governed by not only the physical laws of how our physical capability of literally walking, but all these ingrained unwritten rules in terms of social norms, as well as constraints like walking on a sidewalk versus having a building next to you, so on and so forth. So, so we're actually interested in these 2 application domains as well as others, but this has been the motivation for kind of the fact that we have a lot of stuff that's going on in terms of physics and more traditional, being able to model things with differential equations. And then things that you probably can't model. I can't model a person's decision on whether they're gonna turn right or stop necessarily based on differential equations, right? That might require more of a deep learning type of framework. Okay, so that's been several of the motivating applications in our group. But before we get into some of the methods, I'm going to do a quick detour into a little bit on controls and learning, which is a further motivation for kind of where I'm coming from with a lot of our work, right? So I know some of you are not in engineering and maybe don't have any controls background, so I'm going to give a very, very brief intro to controls, right? And really not even an intro to controls, but the controls community is really interested in looking at basically a feedback system like this, where you're measuring some state of a system, you're using that measurement to update how you control that system, right? So In driving, it might be my steering inputs, my braking, my acceleration. For other systems, you have different kinds of control inputs and different kinds of states that you're trying to control. You measure them, then you update your control strategy accordingly. The controls people are really obsessed with analyzing things like the stability of the system, whether it's controllable, whether it's observable, so you can actually estimate the state of a system. Performance, like how fast does it respond if I change the input? Robustness, can it survive disturbances? Like, so can a cruise control on your car actually recover and respond when it starts going uphill or goes downhill or gets wind from the side, gets buffeted by wind? As well as what's called identification, actually identifying models. So each one of these blocks would typically have either a differential equation or an associated equation in the frequency domain. But really what happens in the controls community is they want guarantees, like mathematical guarantees, that given a certain set of models, I can prove mathematically that the system is stable, controllable, observable, et cetera, right? So that's control 001. For this community, you know, for translational AI, I'm guessing at least some of you are interested in something like reinforcement learning, where here, instead of, let's see if, I don't know if you can see my mouse.
Yes, we can see your cursor.
Okay, so here you would write down, you know, a bunch of equations for your controller and your plant, even your sensor. And that's sort of a model-based approach, right? So instead of writing down a model, reinforcement learning can actually just interact with the environment. So, and the environment could be, you know, your system, if this is a car, as well as other people around you. So environment, air quotes here, this is a general notion. And so an agent would actually take actions, observe what happens, right? So I take an action, the environment actually changes state, or maybe it stays in the same state. I observe what happened to the environment, to what happened to the states of the environment, and then I collect some reward, right? So I might get a positive reward if I get closer to my goal, right? So I'm driving and I'm trying to get to Great Plains Pizza down on Main Street. Check it out if you've never eaten there. Right, and I accumulate a little bit of reward the closer and closer I get to Great Plains Pizza, and then I might get a lot of reward if I actually get there, right? So when I finally get there and turn off the car, then I collect a lot of reward. And then I might be penalized if I get too close to other cars, if I hit another car. If I hit a pedestrian, I might get like a very big magnitude negative reward. And so what reinforcement learning does is essentially tries to learn from that experience, right? So it's going to collect observations and then associate rewards with those observations, and then continue to update how it acts, right? And so the whole field of reinforcement learning, it doesn't even necessarily need a model of the environment. It doesn't necessarily need a model of even what these actions are. It's just going to learn what to do. And it can even, with the advent of deep learning, you can use function approximators like deep neural nets to approximate all this stuff. And you don't need any of these. You don't need to write down equations for everything. Now, the bad part of reinforcement learning is that the kind of mathematical guarantees you get out of it, generally, this is not true, and it's becoming increasingly less true. But generally, the only kinds of guarantees you get are something about convergence that'll actually converge to a policy where my policy is, given a state, what action should I take? And so there are definitely connections between reinforcement learning and traditional control theory. And in fact, if you publish a paper now in a controls venue and it has anything to do with learning, you'll get questions about, is this reinforcement learning? Is this system identification? What's going on here, right? So there's the two communities are getting closer and closer together, which is kind of exciting. I'll skip this one. Actually, let's talk about this a little bit. So another variant of reinforcement learning is that I'm actually, from my experience, going to learn a model, right? And this could be a probability distribution, but I'm going to actually explicitly learn if I'm in this state and I take this action, what's the next state that I'm going to get into, or what's a probability distribution on the next states that I can get into. And I can actually use that model to plan ahead into the future. Right, so this is a slightly different variant of reinforcement learning. And one thing that we've been thinking about in the group is, well, can we use physics in these types of like learning environments, right? So if I already have a good model of the dynamics of my car, can I just use that, or should I use that? Versus when should I use purely learned models? Meaning in this case, mostly for my work, it tends to be deep learning based. So neural networks, for example. And then the question is, should we do both? And I think if we do, how should we do that, right? So how should we connect the traditional field that I come from in mechanical and or aerospace engineering with doing, collaborating with my computer science or CPE friends who tend to use purely learned things. And so one approach to that we've been working on, just a second, is, so I'm going to talk about two different approaches. One is sort of using our physical insights to just predict things. But before I get there, I want to talk about controls a little bit. So there's this paradigm called data-driven model predictive control. So the hypothesis here is that we could do better, and I can define at the end, or at least demonstrate at the end, what it means to do better, if we split what we know from what we don't know. And so I'll give an example what that looks like. But just to give a little intuition, basically what this is going to do is, so say, for example, I was trying to fly from, in this case, Chicago to Zurich. I was giving a talk to at ETH, I think. And so this is an example that what DMPC is going to do is it's going to take any experience, which in this case could be a flight where I fly randomly south and then make some corrections, and I eventually make it to Zurich, and leverage that experience to do better the next iteration, right? So, all right, this wasn't a very good flight, but at least I got there. And if my goal is to minimize the amount of time it takes me to get to Zurich, as well as minimize the amount of fuel that I consume, maybe some other things, that at each one of these little circles, I'm going to keep track of how much it cost me to go from basically here to Zurich, right? So it might take this, might have taken me 3 hours to get from here to here, and I burned this much fuel, right? And then same from this circle, this circle, this circle. So I'm basically keeping track of this trajectory, documenting the cost to go from each one of these circles, and using that experience to basically try to do better the next iteration. And we can basically theoretically guarantee that every iteration within our framework will do better than the last one. And so it would look like this, right? So it'll converge to the to at least a local optimal solution in terms of cost. Okay. All right, so what's actually going on here? I'm going to just do a little bit of theory, not too much, but especially for people who are not in the controls community, this could hopefully be interesting. Okay, so this is data-driven model predictive control. Well, what is model predictive control? So what this does is so model predictive control solves an optimization problem. Okay, and in this case, this is an infinite horizon problem, because I'm basically trying to plan over an infinite amount of time, from time t equals 0, which is now, off to infinity. And I'm trying to minimize, in the controls community, this is called a cost function. In normal optimization, this is an objective function. And then of course, in machine learning, this would be like a loss function, right? And so this function can be anything, but it's a function of my system states. So this could be like the position of my aircraft or my car. and then my control inputs, which in a car is your steering, your throttle, and your braking, right? And I'm trying to min over U. In other words, I'm trying to select a sequence of control inputs from time zero to time infinity that minimizes this function. And then this is subject to a couple of constraints, right? So this is a constrained optimization problem where this is a difference equation in this case, but this could be a differential equation where I'm going to evolve to my next state according to some function of my current state and my input at the current time, right? And this would be like a vehicle dynamics model for a car. So whatever your domain is, typically you could, from a physics-based approach, you would write down a differential equation or a difference equation. I have a starting state, and then I have allowable states, which could be like, I don't want to run into buildings, I don't want to run into other cars, people, so on and so forth. And then I have allowable control inputs, right? I can't apply infinite throttle or infinite steering, right? I have constraints on the affordances of my control system. So I use some type of optimizer to collect basically a trajectory of states of my system from 0 to infinity and control inputs. And then what model predictive control typically does is it selects the first control input, executes it, right? And then you actually evolve to another state, which might not exactly be this because this is an imperfect model. Observe what state you got to, and then it recasts this problem again and does this over and over, which is why this is called a receding horizon control. And there's a finite time version of this where instead of planning for an infinite time, I might just plan for the next 10 seconds, right? Or the next 5 seconds, or whatever it is. So there's a finite receding horizon control version of model predictive control. Okay, so I talked about, well, we want to use physics and learning, or first principles and black boxes. So what we're actually doing in DMPC is a similar problem, but you see now I have this Z hat. And this hat is to indicate that I now have an unknown function. So H could be like a quadratic, it could be quadratic in X, quadratic in U. In this case, I don't even know what it is. It's just, say, a real number coming in from a black box that's a function of X and U, for example. In this case, I'm splitting. So if it's a vehicle application, I might know the dynamics of my car, but I don't know the dynamics of what's around me, right? So there's people moving around. I can't write down a differential equation for them, but I might have a predictive model that's based on deep learning, for example. So this is an unknown function. This is a black box. And in fact, I could have constraints down here in the optimization problem. This is Y hat. This is a function of state, control input, and maybe some noise term, maybe some unknown environmental term that has to be constrained. And the idea is that DMPC can handle this, right? So this could be, I'm trying to minimize the time to my goal to get to Great Plains Pizza, but in a connected vehicle environment, I'm also trying to maximize my packet delivery rate to all the cars around me. And that's coming from this big, deep LSTM model that is just a real number that's flying at me, and I'm trying to maximize that real number. So that could be either an objective here or a constraint. I want to always keep PDR above 0.8, for example. Okay, so I'm going to give some quick definitions. I try to keep sort of the control theory to a minimum here, but there's a couple things that allow us to, some clever tricks that allow us to basically prove that this will work, and it actually works in practice as well. So one is notion of controllable sets. So let's say that this set S is where I want to end up at in the end. So this is Zurich Airport. The one-step controllable set is in one time step. These are the set of all states where I can get from this orange blob to the blue blob in one time step, right? That there are control inputs that are available to me such that I can get from here to here. And then there's an n step version of that where an n could be 10, 20, it doesn't really matter what it is, where I basically get from here to here to here to here, and eventually end up at the one-step controllable step set, and then finally end up at my terminal set that I want to get to. And then there's an infinite version of this where all the way back to, so if I have infinite time to get to S, then this is the set of states that I can start in. And then there are a stabilizable set, and we don't need to know too much about this. The point is, if you know what these sets are, you can do all kinds of interesting math and prove all kinds of interesting things about your controller. The problem is, this is going to be really hard to do for a couple of reasons, right? One is if you have a complex system, it's hard to figure out what these sets are. So that's one problem. So even in the controls community, this is a computationally intractable thing to do for most systems. And then I just talked about how I have black boxes, right? So if I don't have an equation written down, it's going to be really hard to figure out what these sets are. But on the other hand, I can do interesting theoretical things with them. So we're in a little bit of a conundrum. And so like I said here, so one approach to this is to actually do a bunch of approximations and typically leveraging some geometrical notion about how to identify these sets. And yet we can do something interesting, which relates back to the little map thing I showed about flying from Chicago to Zurich, is instead of figuring out what these sets are and then figuring out if I actually have a safe system or if I have a robust system or a stable system, is that I can actually just maybe learn from experience, right? So let's say that this is a trajectory that actually got to this final state and it took 4 time steps. Then I know almost by definition that these 4 X's are part of the 4-step controllable set, right? So this is the 1-step, 2-step, 3-step, and then 4-step. So by definition, I completed a trajectory successfully. So that's in that set. And then I can just keep doing this. And with enough experience, I don't even necessarily need to approximate these sets. But I do something else, which is called the sampled safe set in the lingo. And it's basically, the point here is I'm basically generating a subset of this set that's really important for mathematical purposes. And if you're interested, I'm happy to talk to you offline and show you papers or whatever. But what our algorithms do is they're actually going to leverage this experience in a potentially interesting way. So here is an attempt at sort of graphically showing you what we're doing, and the algorithms are a little bit complicated. I'll show you a little video at the end of the algorithms in action. But what this is doing is essentially, okay, this orange line was a successful trajectory from the very start to the very end at the previous iteration. And now at the next, so J minus 1 is the previous iteration. It's what we did at the previous iteration. And now for whatever reason, let's say I'm over here trying a new iteration, basically a new trajectory. And my planning algorithm has gotten to here. And I'm actually going to do an n-step planning problem. And this green blob right here is basically the n-step, the theoretical n-step reachable step from this point to this green blob. But again, that's a theoretical notion that is very difficult to solve for analytically, let alone approximate. What I'm actually going to do is try to plan to hit in n steps any of these previous points that I got at the previous time step. And I'm just going to keep doing this over and over. And then basically either use this new, basically like, let's see, let's do, yeah, this one's fine. Basically, it's this like recursive algorithm that's either trying to generate a new trajectory that's better than the last one, or just reuse parts of the last one. And so it's a little bit like reinforcement learning where it's using prior experience, but it's not using all of the prior experience. It's just using my last trajectory. So it's, if you're familiar with reinforcement learning, it can be a little bit memory intensive and definitely sample inefficient, right? It needs a lot, in general, a lot of data to converge on a solution. Our solution, because it's using a little bit of control theory and it's using some of the constraints from model predictive control, it's actually able to only use one trajectory at a time. So it's a lot more memory efficient and it's a lot more sample efficient. And one thing that we're able to prove is if you have a feasible solution, then for every time in the future and for every iteration in the future, you will also have a feasible solution. So this is a notion of recursive feasibility, and we're able to prove that. And then the second thing is every iteration will have lower cost than the previous iteration. In other words, it gets better and better in terms of reward if you're a reinforcement learning person. And of course, if you do this enough, you're guaranteed to converge to at least a local optimum. Now, we're not necessarily dealing with convex systems all the time, so this can get stuck in local minima, but you will guaranteed to do no worse than you did at the previous iteration or the previous trajectory. Okay, so that may be a lot of jargon if you don't know anything about controls, but this is an example of how this actually works. Let's see. Okay, so here's a planning problem. We're trying to get from the starting point to the finishing point, and you're trying to basically minimize time and fuel. So this is like this says nonlinear vehicle dynamics is the agent here. And then this contour plot underneath is actually unknown to the controller, right? It can't see this. It's for you to visualize. The only way that it knows sort of the height of the contour, like if these are mountains, is by actually sort of simulating a trajectory and being able to sample. So for example, at this point that I was going uphill, right? And that it was actually expensive to go up this hill, right? So this is the first trajectory. And at each one of these little stars or asterisks, it basically collects the cost to go to the final at that point. So one key assumption is that the controller actually has a first guess that's feasible. The controller knows its own dynamics as well, right? So this is an example of using first principles because it knows its own dynamics, and then a black box, which in this case is just a notional contour plot. But that these contours can actually change as a function of the controller's policy. And that's hard to visualize, so I left this static. But basically, this is the algorithm in action now, right? So it's got this really long trajectory, and it's going to do basically a 10-step planning problem along that trajectory and try to do better and better every time. And so visually, this is what it looks like. So these are a bunch of inner loops, and then it'll create an outer loop trajectory, and you can see it's already optimized. Basically, after 4 outer loop iterations, it's found the optimal trajectory. Okay, so that's sort of what it looks like in action. Again, there's more information in the papers. Case study, again, so here's what it looks like maybe. Where did my, okay. So the case study is, again, back to the vehicle problem where you're communicating. Here's the architecture where vehicle dynamics are known. The communication quality is unknown, but it's predictable by a black box. And here is another video, hopefully this works, of this thing in action on 2 1/10 scale cars in the lab. This is at my previous gig at University of Virginia. Right, so the little white thing is a communication device. And let's see if I can show that again. So it's not, the following car is not like pure pursuit going as fast as it can to the finish line. It's actually also trying to maintain connectivity between the two cars. Because they're so close together, and the strength of the communication signal is so strong, we kind of gamed it such that the communication channel is attenuated. So anyway, so that was a fun application, a fun project to work on. We're actually building some 1/10 scale cars in the lab here if you're interested in that. But the main idea, the main takeaway here is, can we create some synergy between deep learning and other black box models and first principles physics, or maybe other knowledge bases that we can bring to bear on the problem, such that 1 + 1 is actually greater than 2. And so in this case, we have better memory and sample efficiency than reinforcement learning, as well as stronger theoretical guarantees that reinforcement learning. And yet we're able to do something on a larger scale, more complex problem with machine learning than we would be able to do with a traditional controls model. So so that's sort of that thread of work. And then I have a different set of work in the last, I guess, 15 minutes here on prediction, just sole prediction. So that was more of a planning and control problem. And now we're going to get into a pure prediction problem. And eventually part of our work in the lab is to actually combine these two things. So a really hard prediction problem that I alluded to earlier is, people walking around in cluttered environments. And so you've probably all experienced this. If you've flown, you're late for your flight and you're walking as fast as you can, and you're able to do that safely, right? You almost never collide with another person. In the airport case, everyone's going as fast as they can, and sort of an unwritten dynamic happens, and people are to avoid collisions. They're able to sometimes walk in flows, and then the flows diffuse, walking in pairs, leader follower, right? So sometimes you follow someone for a while and then depart. So really interesting problem. There's similar behavior in other contexts, right? So traffic flow problems. We're actually able to do the same thing with ships. So these are, this is blacked out because this is a DoD sponsored project, but so ships in a port that's busy, where you have naval vessels, cruise ships, small recreational boats, even people on paddle boards and canoes, that we can actually use this to model the sort of multi-agent dynamics. Okay, so the hypothesis here is that, again, this comes back to leveraging, in this case, not necessarily physics, but a insight from physics and from experience, is that the influence varies based on the orientation of the neighbors around, in this case, pedestrian or whatever agent, right? So if somebody's directly in front of you, but they're walking sideways, that's going to have a different influence on you than if you're walking in the same direction versus if they're walking towards you, right? So if they're right in front of you and they're walking towards you, you're going to do some type of collision avoidance maneuver, versus if they're walking sideways, you might just keep walking, right? And if they're walking the same direction, then you maybe just follow them and you adjust your speed accordingly to get in sort of this leader follower pair. So that's a simple intuition. And can we just bake that into our models and learn this influence that has to do with both orientation and distance and possibly speed? So the problem here is a little bit more technical detail is, if we're able to actually observe a trajectory, can we then predict in the future, right? So in this case, we're actually able to observe what people are doing for 8 seconds. And the goal is to predict what they're going to do over the next, in this case, T prediction. We can predict actually into 12 seconds into the future. So intuitively, if you're familiar with recurrent neural networks, something like LSTMs or long short-term memory networks could be used to model the future trajectory of the pedestrian. But the problem is LSTMs in this context tend to be temporal, and they have difficulty actually capturing the spatial interactions between the pedestrians or between the agents, if this is cars, ships, aircraft, whatever it is. So the goal here is to actually learn sort of a spatial attention mechanism for these interactions. And we actually borrowed a concept from shipping, which is called a domain, right? So a domain around a ship is basically, if you enter the domain, that means that the other ship has an influence on you, right? So the idea here is to basically, so I have pedestrian 1, pedestrian 2, I have a distance between them, I have a bearing, right? So you might be 45 degrees off to my left, and then heading, which is I'm heading this way and you might be facing 45 degrees, right? So there's distance, bearing, and heading. And that I want to basically model based on those 3 things, whether you are influencing my trajectory. And I want to do this purely based on data. Right? And so the domain, which is a technical term from shipping, we're actually learning using this relatively simple method, which is to basically create a nonlinearity. This S, let's see, use the laser again. I guess I won't use the laser again. Oh, there it is. So, so we're creating a nonlinearity around, this is a learnable parameter that is a function of both the orientation and the bearing of, in this case, 2 pedestrians, and then subtracting the distance, and then taking a ReLU on that. And then that's the weight, that's basically the relative influence between pedestrian 2 and pedestrian 1. And we can do this between all pedestrians in a scene, right? And so think of this as kind of a manifold. This is just one snapshot of a particular orientation and bearing, but you'd get all combinations of 360-degree bearing and 360-degree relative heading. And we take a ReLU of that, and so we have this learnable parameter. And here's an example. This is for ships, where basically it's hard to actually visualize this because it is a high dimensional manifold, but it's basically like, so if you're let's see, if you're in front of me and you're facing towards me, so this is like your bearing is right in front of me and you're facing back towards me, then you're more influential than if you're behind me, for example, right? So ships that are behind this ship are less influential than ones that are in front of it. And furthermore, if you're in front of me and you're facing towards me, then you're more influential. You can see there's a little bit of noise here, and it is hard to visualize, admittedly. Right, so here's an example of if the ship is actually headed sort of in an orthogonal direction, it's going to be most influential if it's sort of out sort of 45 degrees off to my right? Because it's going to go this direction, I'm going to go this direction, and then we'll collide, right? So that's why this is the most influential quadrant. Similar results for pedestrians, right? And this is all data-driven. And I guess the question is, does it work? I'll give a little bit more detail on how this works. Okay, so the architecture is basically every pedestrian in a scene has its own LSTM-based autoencoder. So you basically collapse all the scene information into a bunch of hidden states here, and then you decode that into predicted trajectories. But in the encoding part, we're actually jamming this spatial attention mechanism, right? So this like learned domain thing. So this is a sequence of time. So we have both a temporal notion. So this is the sequence of time. And then I'm basically jamming, okay, it's not just time, it's the evolution of their relative distances, bearings, and headings. That goes into this learned domain parameter S. And then using those learned weights predicts an output. And then the question is, does this actually work? So here's a video of this. The blue lines, this is actually a generative version or a stochastic version, where it's instead of predicting just one trajectory into the future, it's predicting multiple trajectories. So you can see it actually does really well. This at the time, this was from last year, was able to achieve state-of-the-art prediction for people, which is kind of a weird thing. The other interesting thing about this is our model doesn't use scene context. So it actually doesn't know that there's a car here, that there's a sidewalk here, that there's a building. It just through looking at X, Y position and time and using these simple physical insights, it's able to do really good prediction. So then you might ask, well, what if you had the scene context? So that's kind of where we're going next is if you bake in the scene context, can it do a better job of prediction? So next steps in this particular line of work is, or currently what we're doing is actually, can we learn equations, right? So some of you might be interested in, if you're more in the scientific machine learning, is approximating differential equations for human interaction dynamics. And it turns out the answer is yes, we can actually do this. Even though we have all this weird stuff going on in our brain, social norms that might be different depending on where you're walking, is that we can actually kind of learn differential equations for these dynamics and these interactions? And the answer is yes, kind of. Actually, we can outperform the state of the art. But there are some gotchas with that I'm happy to talk about offline. And then the next thing is, can we do this without supervision? So with all these cases, we're relying on ground truth and, you know, the classic problem of labeling all the data is, can we just like observe a scene and give it a learning architecture and learn basically social behavior, like how people do approach collision avoidance, whether they walk in pairs or groups, whether they're leader followers. Can we actually learn those behaviors without telling the machine that it should do that? And then so I'll start wrapping it up just for some other interesting things to me in terms of application. So this is an air traffic control simulator. So we're interested in future air mobility, advanced air mobility concepts, and using these simulations to improve decision making, in particular with safety critical applications, right? So that tends to be, I work in things where if you make a bad decision, it can kill people or cause a big financial loss. And then another thing is how humans and autonomy interact and how that impacts safety. So how we allocate authority and responsibility to different decision-making agents, whether they're human or machine. So with that, almost out of time. I didn't leave enough time for questions, but I will flash these are a few sort of selected papers on the type of work that I presented today, and then a couple interesting papers, I think. So now I'll leave it up for questions. Sorry, I didn't leave enough time.
Okay, thank you, Cody. Questions? Any?
Yeah, Cody, I have a question for you. This is Dan
Yeah.
Middleton from Statistics. Maybe this is more of an observation than a question, but I was just thinking, one of the things I'm interested in is sports analytics. And I think it would be interesting to predict the trajectories of humans when they're trying to be deceptive, which happens all the time in sports applications, right?
Yeah.
That would be a much harder problem, I would think, than like, watching somebody walk on the street. And so anyway, that's just a comment, I guess, but I think that would be an interesting challenge. And then I guess the question is, when you showed multiple trajectories, can you make probabilistic statements about, like, I mean, can I think of it like a prediction interval, like they're with confidence of 95%, they're going to be within the limits, or are these just, can you talk a little bit about what those multiple trajectories mean, what properties they have?
Yeah, so it does come with, so we have like 1,000 different variants of this. So there is at least one variant that comes with probability distribution, and there is a Bayesian version of this too that is more of like, how confident am I in this, that, or the other. Related to sort of both your comments is there's another thing that we're trying to do that's actually really hard, is for planning purposes, is that I don't want to just it might not be the best thing to even predict exactly what I think you're going to do next. Is to actually have multimodal prediction, where you could do like 3 totally different things. I might turn 90 degrees right, I might go straight and speed up a lot, or I might just stop in my tracks, right? And that I actually want to be able to predict all 3 of those things. And then I might have like a risk averse planner that says, okay, I'm not confident in any of these, so I might just, like, if it's an autonomous car, like veer off to the left and just avoid this person entirely. That actually relates to the athletics part, right? Where it's like, you could condition on, like, if it's football, like, this is the setup, there's 5 different plays they might run, blah, blah, blah. And then there's also, we're trying to tie the 2 different threads that work together, the planning and control and prediction. And the fact is, like, what I do is actually going to influence what you do, right? So if I keep going straight, you have those times where you're in the hallway and both people are, I'm going left and you're going right, so we go like this, right? And it's like, oh, sorry. There's a game theoretic notion here too, of how all the agents are actually influencing each other, that this method by itself doesn't necessarily consider, right? So that's a hard problem that we're trying to sort of unpack right now.
Cool. Okay, I got to drop off, but nice talk. Thank you.
Yeah, thank you for being on.
Thanks, Cody. I know we are out of time, but at some point I wanted to ask you this, that, I mean, you worked with both, MPCs and RLs. I mean, as a practitioner, a practical use of both of these, what do you see the pros and cons? I know it may be a longer discussion, so we could take it, but I often think about it. I mean, I back in the days I used MPC, and it can be a nightmare if it is a high dimensional problem. It's a lot of large cost function. Computationally, it could be a nightmare. But we also know about RL, running into a lot of sample complexity issues. So I wanted to know from your practical experience about the pros and cons, but we could take it.
Yeah, I mean, I guess the short answer is you kind of said it, right? Is like, they both kind of have their own. MPC, they don't talk about hyperparameters, but they do have them, right? It's what should my height? You change your planning horizon by like 1 increment, and it totally like either breaks it or makes it work faster. And so I think
even just running the optimization to convergence every time, I mean, that itself. Could be
yeah, and I think some of the solvers are getting a little better at that, but so I think, like, I'm not a big believer in like a one-size-fits-all answer in general. It sounds like you aren't either. So it's sort of like, you have to, from a practical experience, you have to play around. There's general guidelines. If you're able to get a lot of data, then RL is probably a good way to go. But then there's a lot of times a transfer problem, because the way to get data is through simulation, and you have to take it in the real world. So anyway, happy to talk about that more.
Let's share at some point over a coffee.
Cody, I have a question about this PC model. Looks very interesting to me. Just any network problem can be written that way. But with the constraints involved, how do you train that? I think a computationally efficiency could be an issue. Also the convergence. You see, you have a constraint. The control is in some domain. And you have other like a white hat is all additional constraints beyond that from one time to the next.
Yeah.
How do you train that typically? Actually, I'm considering the network is similar problem, similar formulation, trying to understand mathematically how to design algorithm to make it fast and more.
Yeah. So we're actually, I should be clear here. In this problem, the training of, so these like this Y hat and Z hat, these are deep learning models. But they're actually not trained with this system. They're trained in a separate, so let's say they're trained offline. And then given my current state and my current inputs, it'll just spit out whatever it spits out, right? So it's, and here we have the only constraint we have on in this case is that it puts out a real value. We have another version where it actually has to be a positive definite function. So the neural network always has to put out either 0 or a positive number, and it'll still converge. But it's actually not doing online training with the controller. So it's basically totally separated out the two problems, which is a bit contrived, but it actually applies for a lot of the problems that I work on.
But typically, how do you take the time step? You don't take infinity, right? Just find a number of steps.
Yeah, so typically this is actually back to Silmic's question of like this number right here. I don't know if you can see my mouse, but infinity is typically not infinity, it's n.
Depending on which you have.
Fixing that n actually totally changes the optimizer sometimes. So that can be problematic from an application perspective, but usually doesn't matter for the theoretical side.
Okay. Okay, I think one last one you mentioned learn dynamics without supervision. But my understanding, mathematical point of view, if you have a dynamics equation, is well posed, then you don't need any supervision because you need to get everything from that problem itself. Try to develop an optimal strategy for that. So am I right? It's maybe you mean something else.
Yeah,
what do you mean?
So this would be like a purely black box problem, right? So in other words, I don't know. So in the context of like pedestrian dynamics, I can't really imagine writing down the equations ahead of time for that. So this is like, can I basically learn the system without any like labeling of data?
Oh, I see. You have let's see.
So I don't know.
Yeah.
It'd be interesting if I don't know. I have to think about that more because there are applications where you do at least have a structure of the equations, and then things are more constrained. And then like we talked in your office about like, can you identify the equations is another thing that we're trying to do.
Yeah, that's a really interesting area. Yeah, think about it.
So that's hard. We're actually doing it for traffic flow dynamics right now. And we're getting some decent results. When they, hopefully the results get a little bit better and I'll share it with you.
Okay, good. Well, thank you. Any other question?
Yeah, Professor Cody, I have a few questions. So you mentioned about this MPC controller. So I'm questioning is if I have very good planning stage, for example, my planning is like a RT and my controller just a POC, a PID controller. So would it like more computational efficiently to compare with this MPC controller? What do you think?
Yeah, that you're actually getting at something really subtle with this word, which let's see, is so one thing, this is actually really efficient. It's probably not more efficient than RRT, to be honest. Now the one thing is this is like, so in this case, this contour plot underneath is dynamic and unpredictable.
Yes.
And it's also influenced by my own strategies, kind of like these game theoretic things. That RRT can't really handle that directly, but it can handle, it's fast, right? It works really fast.
Yes.
It could be that you just do it over and over and
Yeah.
until the thing stabilizes, and then that's your trajectory.
Yes.
So that we haven't done a comparison of like computational complexity on that.
Okay.
But I do think that there are pros and cons, right? So
Sure. Yeah.
it's a very, very good question though.
Okay, and I have a second question. You also mentioned at the beginning, mentioned about RL and some optimization questions. Yeah, I understand RL is also like so as Dr. Saka also mentioned about like even some like RL like problem like DDPG, they also use like minimize the loss, minimize the returns about the Q values, something like that. So like when you compare with RL or like all these higher controllers, like how do you like in what case you will like distinguish these two different methods, or how you choose to use?
Yeah, you sound like a reviewer of our papers. So I think I think everyone is slightly confused by this, right? Because there is a good. It's actually related a little bit to Somik's question of like, and your question,
because
right?
yeah, because I recently look at quite a lot of like RL problem and not really deep into the MPC. And when you bring this topic, it's very, very interesting to me actually. Yeah.
Yeah, I think like even your question about RRT versus MPC versus is you know, there's some, you could think about it from a complexity standpoint, but there are not a lot of good ways to actually compare. There isn't like one metric where I know that this is better than the other thing, right? Because there's how long it takes to train, how fast it is at runtime, how much you might know about whether at runtime it'll give you a good solution or not, and so on and so forth, right? So there's a lot of different characteristics that you want out of a system that it's really hard to make one comparison. And I think every paper on this that we've submitted has gotten this question. I think everyone's okay with like, we don't exactly know how to even have this conversation in a rigorous way yet, but I'm happy to chat with you. Shoot me an email after.
Sure.
I actually have class. I have class right now.
Oh yeah, sorry.
So sorry, I have to go.
Yeah. Thanks a lot.
We'll use more time. Very interesting discussion. Thank you, Cody.
Yeah, thanks a lot. And if anyone has more questions, just send me an email and
sure. Yeah, we talk more. Yeah.
Okay. Thank
Bye-bye,
you,
everyone.
Bye.